we present PCDreamer, a novel method for point cloud completion through multi-view diffusion priors. First, let's begin with a brief introduction to the background of point cloud completion. Our work focuses on single-view partial point clouds with self-occlusion. As shown in the first two columns of the figure, the self-occlusion often leads to the loss of more than half of the 3D shape, which implies a vast solution space for completion. Most existing methods, such as C or APCN, rely exclusively on partial point clouds as input. This limitation often results in random local gaps in large missing regions, such as the critical top holder of the lamp. To address this, some approaches, such as SPDeformer, incorporate additional image information to improve completeness, but they often rely on depth images projected from partial point clouds or RGB images, which are hard to obtain in practice. Motivated by the success of diffusion-based image generation, we observe that the relatively view-consistent multi-view images generated by large diffusion models provide rich global and local shape cues, which are particularly advantageous for shape completion. Here, we present the multi-view images generated by 1to3D. This slide presents the pipeline of PCDreamer. Given an input partial point cloud, we have designed 3 core modules to complete it. The multi-view image generation module dreams out multi-view images of the input by leveraging a few large models. The priors within these models serve as the fuel for the completion. Specifically, the conversion from a single-view depth image to multi-view depth images generally involves 3 main steps. First, the single-view depth image is used to generate a corresponding RGB image with the help of ControlNet. Next, a multi-view generation model such as 1to3D or stable video diffusion is employed to synthesize multi-view RGB images. Finally, a monocular depth estimation method is applied to obtain the corresponding multi-view depth images. The Diffusion module effectively fuses the original input and the inspiring multi-view images with the help of the attention mechanism. A final consolidation module further refined the coarse point cloud, producing a complete, dense, and uniform point cloud with both the global and local shape features. Specifically, to mitigate the inherent inconsistencies introduced by large models, we propose a confidence-based shape consolidator that operates on the fused features to filter out noisy points with low score. Our network is trained end-to-end with the chamfer distance space losses. To combat noise and outliers, we exploit the extra hyperbolic chamfer distance. Specifically, we measure the discrepancy between the ground truth point cloud and the coarse and final point clouds, respectively. In the experimental section, we will present both statistical and visual results on PCN and ShapeNet dataset. The quantitative results on the PCN dataset demonstrate that our method outperforms all previous approaches across nearly all categories, while achieving the best average performance. An exception is the lamp, where C or APCN achieves slightly better performance. The inconsistency in the multi-view image generation module, especially when the lamp's support structure has a folding line or curved shape, leads to lower accuracy in our method. The visual comparison in several selected categories show that our method can predict the missing parts more accurately due to the additional shape cues provided by the generated multi-view images. Particularly, for airplane category, all other methods fail to complete the missing symmetric parts, such as the engines, while our results are more consistent with the ground truth. Besides, we also present the generated multi-view depth images on the PCN dataset. In the upper table on this slide, we select the 10 representative classes from a total of 55 categories to showcase the chamfer distance. Our method consistently outperforms other state-of-the-art approaches across all categories. Although the first 5 classes contain significantly more samples than the latter 5, we have obtained comparable results across the 10 categories, which demonstrates the generalization ability and robustness of our method on diverse types of data. The lower table displays the statistical results on the ShapeNet 34 dataset, where our method maintains high completion quality on unseen compared against state-of-the-art methods, demonstrating moderately strong generalization ability. The visual comparison on the ShapeNet 55 dataset also clearly illustrates the superior performance of PCDreamer on complex shapes with finer details. In conclusion, we have presented a novel approach for point cloud completion. We introduced diffusion priors in this task to provide imagined full shape cues for free. From this proof of concept, we believe that diffusion priors can be useful for other point cloud processing tasks, and we hope PCDreamer can inspire future research in this direction. Thanks for watching.